Okay, so if you could please find your seats, we're just going to start with the last talk of the day. So it's a pleasure to introduce Thomas Vidick from Caltech, who's here to tell us about a multi-prover interactive proof system for the local Hamiltonian problem.
Thanks, Andrew. Can everyone hear me? Is the mic moving? Yeah, I was going to fall. This is good, right? Is it? Okay. All right. So it's a pleasure to be here. Thanks, Andrew, for putting the pressure on me by reminding everyone that this is the last talk of the day. So better deliver. Everyone stayed just for that. So I'm going to talk about some joint work with Joseph Fitzsimmons, who's in Singapore. And it's kind of around the same kind of issues that have been discussed through the day today. These questions of relationship between local properties, locality, and the global properties or global structure in quantum states. But I'm going to use a very different language than the ones that's being used today, so I hope to draw you into my own language, which is we're going to be thinking of quantum states as proofs or interactive proofs for quantum states. So I'll explain what I mean by that in the talk. So here's the outline. First, we'll talk about these interactive proofs in the classical setting. Then I'll introduce you to the quantum setting. This is quantum multiplayer games. I'll present our result. And if I have enough time, I'll tie this to something called the quantum PCP conjecture. So let's start by something which maybe everyone is already familiar with, which is the problem of checking proofs in the classical setting. So everyone's seen the class NP. Here are some examples of NP complete problems. So clique, chromatic number, you've seen. Ising spin, lots of you have seen. And some maybe more exotic ones, pancake sorting, Super Mario. Wikipedia has a very, very long list. The reason I'm putting those up is that to try to make it a little bit more surprising, the famous Cook-Levin theorem, which says that the class NP has complete problems. So what this means is that there are certain problems, such for instance, 3-SAT is the canonical example, that are just about as hard as any problem in the class NP. So for instance, if you start with the 3-coloring problem, any graph G, you can transform into a 3-SAT formula, such that the graph is 3-colorable if and only if the formula is satisfiable. This is saying something about the structure of all problems in NP. All of them can be verified locally, just as 3-SAT. So what do I mean by the fact that 3-SAT can be verified locally? So let's think about this. So this main character, Arthur. Arthur is given as input a 3-SAT formula. Actually, he's given as input a graph, wants to decide whether the graph is 3-colorable or not. So what the Cook-Levin theorem is saying is that given the graph, you can efficiently transform it into a 3-SAT formula, something that looks like this. And now you want to decide if the formula is satisfiable or not. So this remains a hard problem. This is why we need the help of the second character, Merlin. Merlin can provide you with a proof. So in the case of 3-SAT, this would be an assignment to the variables, such that if the formula is satisfiable, then the assignment will satisfy all the constraints. If the formula is not satisfiable, there's no such assignment. And now Arthur can verify this proof locally by simply choosing one of the constraints at random. So here he chose constraint number 10. This constraint acts on 3 bits, 3, 5, 8. He's going to look up the value of these bits, check that the constraint is satisfied. And if it is, then he'll accept. If it's not, it's reject. So that's the kind of proof systems that I'm going to be talking about. And there's two important parameters of a proof system, the completeness and the soundness. So the completeness is the probability that, the completeness is in the case where you have a yes instance, so where the formula is satisfiable, the maximum probability with which Merlin can make you to accept. And in that case, the completeness is 1, because if the formula is satisfiable, there's a satisfying assignment, and I'm always going to accept satisfying assignments. The second parameter is the soundness. So that's the maximum probability with which Merlin can make you accept in case of a no instance, in case of the formula is not satisfiable. And in the case of my proof system, the soundness is not that good, because if the formula is not satisfiable, it's just saying that any assignment has to violate at least one of the clauses. And because Arthur is just checking one clause at random, the chance that he picks maybe the only one clause that's not satisfied is pretty small. It's just 1 over the number of clauses, so 1 over m in this example here. So the soundness is only 1 minus 1 over m. In general, you'd want the soundness to be better so that there's smaller probability of Arthur making the wrong decision. But it's not going to be a parameter that I want to focus on too much in the talk. So it's an important parameter, but it won't come up so much. For my purposes, a proof system is valid as long as the completeness and soundness are different. Right? So if you should accept, you accept with a higher probability than in the cases that you should reject. Rather, the question that I want to focus on is when is it the case that we can really say that this is a local verification, local proof verification system for 3-sat. And here I want to say this is not quite local verification. True, I'm only looking at 3 bits, but in the first place, Merlin had to give me this whole proof, right? I didn't look at the whole thing, but he gave it to me. It's there. I need at least the memory, the amount of memory I need is pretty large. So I want to ask if you could make this into a truly local proof system where you don't need to receive the whole proof in the first place. So something that would look like this. I send the proof back to Merlin, and instead I try to do the same thing. I pick one of these clauses at random. It acts on 3 variables, and then I'll just ask Merlin directly for the values, right? What's the value of x3? He's going to tell me 0, x5, 0, x8, 0, and it works out. My clause is satisfied. So now I claim that this proof system is not valid. It doesn't have completeness and soundness that are separated. Hopefully everyone can see this. Here there's always a way for Merlin to cheat. The problem is that I'm telling him what clause I'm interested in, right? Maybe the first time when I ask him about x3, he doesn't know yet, so he says 0, x5, he doesn't know. But then the moment I ask him about x8, he knows I'm interested in clause number 10, and then he can change his answer depending on what I've asked him about so far. So this doesn't work, right? And that's kind of interesting because in the original proof system, I wanted to say I only queried 3 bits, but still it was important that I had the guarantee that the whole proof was written down and was not sort of changing as I'm making my queries. If I give the proof back to Merlin, he can change his mind on his answers to later queries, and that's messing up my proof system. So let's try to fix this, and there's a way to fix it, which is the model of multiprover interactive proofs now, which is going to involve not 1, but 2 Merlins. And I'm going to sort of switch between the language of interactive proofs and games. So these characters, I'll call them Merlins, I'll call them provers, or I'll call them players. It's the same thing. It's sort of useful to think of this as a game. It's also the last talk of the day, so it's more fun to be playing games. So we'll think of the Merlins as players, Arthur as the referee who's asking them for questions. And just as before, Arthur is just going to try to check the validity of a 3-sat formula that's given to him as input. And then I'll define a game. So let's try to do a game. For 3-sat, it's called the clause versus variable game. The reason is it proceeds as follows. First, we do the exact same thing as we did before. So we have this formula, m clauses. I choose one of the clauses at random, and I ask Merlin number 1 about it. And he tells me. And of course, he's going to tell me something that makes me happy. So this is always going to work. This satisfies the clause, just as in the previous slide. But here's where the second Merlin comes in. We're going to check him, to use him to check that the first Merlin is giving us answers that don't depend on the clause that I'm asking him about, only on the specific variables. So what I'll do is I'll take one of the 3 variables, 3, 5, or 8, and ask second Merlin about that variable. And he has to give me an answer that's consistent with the answers of the first Merlin. So here he messed up. This is wrong. I'm going to reject this. So my claim is that this proof system now is a sound proof system for 3-sat, and it's not hard to see. So if the formula is satisfiable, of course the 2 Merlins can agree on a satisfying assignment and always answer my queries according to this same satisfying assignment. And these answers will always be correct, and they'll always be consistent with the second prover's answers. So I'll always accept. But now let's assume that the formula is not satisfiable, and let's try to argue that it's impossible for the Merlins to win with probability 1. There's many ways you can see this. One way to see it is to use the second Merlin. Because what does second Merlin do in this game? I ask him always only 1 variable at a time, and he gives me 1 answer. So in his mind, somewhere lies a set of answers to the questions I can ask him, and the set of answers to the questions is just an assignment to the variables. So this Merlin, in his mind, has a proof. He has an assignment. And because he always has to be consistent with the first prover, the first prover also is constrained to answer according to the assignment that second Merlin has in mind, which means that the values that he sends me back to me now are consistent with this, and because I checked that they satisfy the clause that I asked him about, then this assignment should satisfy the three-side formula, except with small probability. We lost a factor 3 here because of this consistency that we're doing. So I'm using sort of second Merlin to hold the proof for me in certain way compared to what I was doing in the first slide. But now this is truly local because I don't even know, no one is telling me that the assignment exists. It's there in the sky, it's in the Merlin's mind. I'm sending them questions, and the total amount of information that I'm receiving back from them is at most 4 bits. That's it. But that's enough to check that the formula is satisfiable. Except for this little, the fact that I make mistakes with pretty high probability, 1 minus 1 over 3m, I make a mistake. So it turns out that you can do much better, and this is it's a result called the PCP theorem. It's a major result. It's a very hard theorem to prove. But you can sort of boost this proof system that I described to you in order to keep the completeness same property as we had. But then the soundness, if the formula is not satisfiable, then Arthur is going to reject with probability half. And you can make this arbitrarily close to 0. So you can amplify the success probability efficiently. But I'm not going to describe how this is done. For our purposes, we're more interested into going and trying to understand if you can do the similar things in the quantum case, right? So let's do something quantum. So the first step is sort of well known. This is class QMA, quantum analog of NP. It also has complete problems. The canonical complete problem is quantum circuit sat. Does a quantum circuit have a satisfying starting state or not? Another one is this unitary non-identity check problem. And then there's a local Hamiltonian problem that we've heard a lot about today. So because it's important for the talk, I give you a formulation here. I'm actually cheating a little bit for the experts. This is like the frustration-free version of the 3 local Hamiltonian problem. It's just more convenient for the talk. So I'm going to look at 3 local Hamiltonians. Each of my local term is a Hermitian matrix. It's positive, semi-definite. It has norm at most 1. And the problem is to decide whether this Hamiltonian has smallest eigenvalue 0, or if the smallest eigenvalue is at most a small threshold. Inverse polynomial in n. N is the number of qubits here. Also the number of local terms, well, it's at most n cubed, because I'm looking at a 3 local Hamiltonian problem. Just to be careful with respect to the talk by Mario Zegedi before, there's no gap here. My Hamiltonians don't have a spectral gap. I'm only going to be talking about the smallest eigenstate, so the ground state. I'm not assuming any gap above the ground state. This is something different. It's a promise. I'm saying either the lowest energy is 0, or the lowest energy is 1 over n or 1 over n squared. But be it the first case or the second case, I'm not imposing any gap on the Hamiltonian. So the kind of ground states I'm going to be talking about can be very highly entangled. There's no real law, no such thing here. So I hope I didn't introduce more confusion than I removed by saying this, but so forget about a real law for the purposes of this talk. And so the important theorem, right, is the one that's hidden between the normalization by Kitaev, which is to say that this local Hamiltonian problem is complete for QMA. So again, all these problems have local verification procedures in the following sense. So if I'm Arthur, I'm given a problem instance such as this. So this is an instance of the non-identity check problem. I can transform it into an instance of the local Hamiltonian problem in a way such that now Merlin can provide me with a proof. So in that case, it will be a candidate ground state. And I can verify, sort of estimate. If Merlin is claiming that this ground state has energy 0 with respect to my frustration-free Hamiltonian, what I'll do is that I'll choose one of the local terms at random, let's say the 10th term. This 10th term acts on 3 qubits. I can look up the 3 qubits. I can perform, this is why I chose this normalization there. I can perform a binary 2-outcome measurement that, the POVM elements are hi, 1 minus hi. And if I get hi, then I'll reject. If I get 1 minus hi, I'll accept. And so in case the ground state energy is 0 and psi satisfies all the constraints, then I'm always going to accept. If the ground state energy is inverse polynomial, there's always going to be at least one term that's slightly violated, and there's going to be a small chance that I detect this. So in the case where the instance is negative, then I have a small problem to reject. So this is a sound proof system, but again, same problem as before. I need to have this proof given to me, even though I'm only looking at 3 qubits of it. So we can ask the same question as before. Could I give the proof back to Merlin and have a truly local verification procedure for the local Hamiltonian problem? And so the purpose of the talk is to sort of try to investigate this question and give answers, or see what kind of answers we can give to the question. If there's any question for the speaker, I can pause and answer the question. Otherwise, we'll just continue. Try to adapt the same framework we had in the classical case to the quantum case. So we're going to be talking about quantum multiplayer games. So just take the same thing as before, make everything quantum, see what happens, right? So now we have a quantum Arthur. This quantum Arthur exchanges quantum messages with the Merlins. So it looks like something like this. You can send them qubits if you want. They can send you qubits back. So that's the first modification that I make to my games, quantum communication instead of classical communication. And there's a second important modification that we're going to make, is that now that everyone is quantum, it makes sense to have quantum entanglement. And so the quantum Merlins may also be sharing entanglement in this game. And so now, given a description of the game, I'm interested in the maximum success probability that quantum Merlins, possibly sharing quantum entanglement, can have in the game. What's interesting about this model compared to the purely classical model is that the two modifications that I made can have sort of opposing effects. So on the one hand, I allowed quantum communication, and that's clearly more power to Arthur. He can do more things. He can ask sort of more complicated questions, send quantum states. He can also get more information back from the Merlins because they can send him back quantum information. If Arthur wants to keep everything classical, he can do that. Only send classical bits, maybe get quantum messages back, but measure them in a computational basis, and then there's no point in Merlins for sending in quantum messages. That's definitely more power to Arthur, and this is good because I'm trying to use these games or proof systems to verify QMA complete problems, whereas before I was doing only NP complete problems. But in fact, it's known that this is not enough by itself. So if the only modification, forget about entanglement, if the only modification I was to make is to allow for the exchange of quantum information, there's no way I could verify local Hamiltonian problem in this model, unless QMA equals to NP. So that's a result by Kobayashi and Matsumoto. So this is where the second modification comes in play. And it's interesting because when you think about these games, at least people like me who think about these games, we're used to thinking about the fact that I give entanglement to the Merlins as giving more power to Merlins. This is also sort of the perspective from Bell inequalities. We're saying, okay, you guys have entanglement, means you have correlations. Using these correlations, you have a larger set of strategies. So you're going to be better at playing my games. In particular, you're going to be better at cheating. So kind of proof systems that were sound before might break down in this model. But the talk now, I'm going to take a different perspective. I'm going to say, well, maybe this is more power to the Merlins. This is also more power to Arthur in a certain way. He knows that the Merlins have this entanglement. Maybe we can take advantage of that to design new proof systems that did not fall in the previous framework. And what the Kobayashi-Matsumoto result is saying is that we have to. We're going to have to walk outside of the framework that we had before. So let's try to do this. Let's try to do the quantum analog of the clause versus variable game that I described before. Let's have a Hamiltonian versus qubit game. So here's the goal. For the remainder of the talk, this is what we're trying to achieve. We're given an instance of the local Hamiltonian problem, and we want to decide, is the ground state energy 0, or is it at least above a certain threshold? We're trying to design a game that is going to distinguish between these two cases. For this, we have access to these two Merlins. And so here would be the natural thing, right? Just I'm mimicking what I did in the classical setting. Arthur picks a local term, so just one of these local Hamiltonians. He asks the first Merlin about the Hamiltonian, and then he picks one of the qubits and asks the second Merlin about that qubit. Now, each of these Merlins has in their mind the ground state of the Hamiltonian. This Merlin is going to send me back 3 qubits on which this term acts. He's going to send me back the 1 qubit, and then I'll check the kind of things that I checked before. So I'll make the measurement on these 3 qubits, and then I'll check that the answers that these 2 Merlins give me are consistent. So now what does that mean, right? Yeah?
Simple question. So the Merlins are sending reduced density?
Good question. They could, or they could just send me the actual qubits. So, but these qubits will be in a mixed state in general. Yeah. I could ask them for both. I could ask them for the quantum state and maybe even a classical description of the quantum state, because this is a 3-qubit density matrix, so it doesn't take so much space. I would still say this is a local proof system because it takes 100 bits to specify or something like this. Still, I run into trouble here because actually you're going to help me. So if in the case where they were only sending me the qubits, really the quantum bits, how do I check that the answers are consistent? Probably, these 3 qubits are in some mixed state. This is also in some mixed state. Doesn't mean anything to check that the 2 of them are consistent. Except if they give me a classical description, then I can take the classical description of the reduced density, trace out the qubits, and check that the reduced density matches what reduced density this guy provided me. So this was in the case of qubits. But then even if they give me the specific densities, this is not going to work out, right? Because the state is really highly entangled. It's pretty likely that all these reduced densities, they're totally mixed. 1 qubit, 3 qubits is a totally mixed state. Sure, they're consistent, but is that implying anything about the ground state? No, actually it doesn't, and I have a proof of that, actually a complexity theoretic proof. Because my proof system so far is not requiring the Merlins to use any entanglement. And I told you before, if we don't put entanglement between the Merlins, there's no chance that this can work, because we can only verify languages in NP. So unless you think that maybe NP is equal to QMA, unless you think that the local Hamiltonian problem is in NP, which we don't think, there's no chance any such thing is going to work. So not this one, not any other one. We have to use entanglement between the Merlins. So another idea would be, here the problem I have is that I said each of them has a separate copy of the proof. So let's use entanglement in order to tell them why don't they split the proof in between themselves. Okay, so that's where the picture comes into play. Some of you were wondering, why do I have this picture on the board, on the slide before starting? So I'm going to try to make you feel what is the difficulty that Arthur is facing. So in the classical case, we were trying to check that there exists a global assignment to the variables of a 3-stat formula that satisfies all these local constraints. And we managed to do this, and it's because classically, things are okay. If you read a picture like this and you look at only 1 bit at a time, then it's not so easy to check that things are consistent, right? Here you're seeing a body, a human body, or maybe it's a forest. Fine. There could be a human body there, right? Here you're seeing the front of a house. Fine. Yeah, there can be a house. This can be the sky. This can be a curtain. This is fine, right? But as soon as you start asking 2 of them at the same time, then it's, you start detecting that something's wrong, right? There wouldn't be like a forest on top of a house. That doesn't make sense, right? So then you've detected that the global picture, you can't put these local views together just by checking them 2 at a time. So that works classically. In the quantum case, if you try to do the same thing, you ask, what's my state here? Well, it's totally mixed state. Something that's highly entangled with the rest, totally mixed state. Okay, fine. Also, you can look at the picture 2 by 2, and this is supposed to be an EPR pair, this is supposed to be an EPR pair, fine, this is supposed to be an EPR pair, fine. All these EPR pairs, what I didn't manage to detect so far is that there's no way to have 4 EPR pairs like this, right? This picture doesn't make sense. The question is, how high up do I need to go in order to detect that the picture doesn't make sense when I'm making the local observations? And that's the difficulty. This is sort of a harder problem to do in the quantum case. I'm going to give you a way to solve the problem in this, in this context, but it's a question you can ask very broadly in many different contexts. So what's the result? The result is a game that's going to let us differentiate between these two cases of the two instances of the local Hamiltonian problem. Right, so actually the first time I gave this talk, with Joe, we had a 5-player game, and then people in the audience, I think one of them was Dan, he left maybe, Daniel Gottesman pointed out that we could do it for 3 players. But I'm still going to use the 5-player description because it's easier for my purposes. So here's what I'm going to give you. It's going to be a game that involves the quantum Arthur, and not 2, but 5 quantum Merlins. The game will have the following form. Actually, the questions will be classical, so the information from Arthur to the Merlins will just be very simple queries. Each Merlin is going to send back 3 qubits, no classical bits, just 3 qubits each. And it'll be such that these properties hold. In terms of complexity theory, there's some interesting consequences to the result, but I'm not going to go into them too much. One consequence, though, is that computing or estimating the maximum success probability of Merlins in this kind of game is a QMA hard problem. So this is better than what we knew before. Before we only knew that it was NP hard. It has a consequence in terms of interactive proofs that I'm just stating here for those of you who've seen these interactive proof classes before, but I don't even want to explain what the symbols mean. You can ask me about it if you want to know. If I have time, I'll get back to it, but this is just for the experts. So that's the result. Let me describe what the game is now. See, before, let's see. So this is what it's going to look like. So here's how I'm going to split the proof. Instead of giving, instead of giving each Merlin 1 copy of the proof, or splitting the actual proof and saying, one Merlin has half the qubits, the other has half, here's how we're going to do it. I'm going to take each qubit of the ground state. This is what I'm asking the Merlins to do. They can do what they want, right? But ideally, I'd like them to do the following thing. I'd like them to cook up the ground state of the local Hamiltonian, take the qubits of the ground state 1 by 1, and use a 5-qubit error correcting code in order to split that qubit in between themselves. So they each get 1 share of the encoding of 1 qubit of the proof. And then I'm going to run 2 tests, each of them with probability half. One of the tests is sort of the straightforward thing. I'm going to choose a random constraint. This constraint or local term, this constraint acts on 3 qubits, and I'm going to ask every single Merlin for their share of that qubit. Right? Each of them has a share distributed according to the code. I ask them for their shares. I get all their shares back. I decode the error correcting code. I perform the measurement that's associated to my Hamiltonian, and I check whether I see an energy that's 0 or pretty close to 0 or something that's wrong. That's just the obvious thing. The slightly less obvious thing, although now that I described what honest Merlins are supposed to do, it's also kind of clear. What I'll do is that I'll again choose a random term that acts on 3 qubits. I'll ask one of the Merlins for his share of the 3 qubits. And here it's important that this particular Merlin here can't distinguish if I'm running test number 1 or test number 2, right? He's asked about 3 qubits that are involved in a certain local Hamiltonian. So he has to do the exact same thing. Now the other 4 will be able to distinguish between the 2 tests, but that's not so important. What I'll ask about the other 4 is just for their share of a single qubit. What's important about them is that they don't know that I'm interested in term number 10, they only know I'm interested in qubit number 5. They have to send me the shares back, and the test that I make is that I just check that with respect to qubit number 5, the 5 qubits that I got lie in the code space. So I just make a code measurement. So the completeness is okay, right? If the local Hamiltonian instance does have a ground state with ground energy 0, then there is a way for the Merlins to always satisfy my answers. And I'm going to try to argue that soundness holds. And just to give you the intuition of where the code property comes into play and why actually it's not necessary that it's an error correcting code, simply an error detection code is going to be enough. How am I going to use that? Well, here, imagine that something bad happens. What is something bad? Something bad is when this Merlin here, the one that was asked to 3 queries, this Merlin here sends me back answers that depend not only on Q5, such that qubit number 5 depends not only on Q5, but also on the fact that I asked him about Q3 and Q8. What do I mean by this? I mean, well, if I had asked him instead for Q5 in conjunction with something else than 3 and 8, but maybe 2 and 9 because of some other local term, he would have sent me back another qubit, another value for Q5. But if there's 2 different possible values for qubit number 5 that this guy can send back to me, depending on his queries, then the 2 possible, just because they're different, the 2 possible values can't, both of them, lie in the code space with respect to the 4 qubits that the 4 other Merlins are committing to. So that's where the error detection property is being used. These 4 Merlins are committing the answer of Merlin number 5 for him. By sending these 4 qubits, then because of the code properties, there is only one possible sort of valid answer for Merlin number 5. That's sort of the intuition. I have a slide trying to explain a little bit what could go wrong. I don't know if I want to get too much into that. Sorry. Yeah, let me try to give you an idea of one thing that could have gone wrong. I'm sorry. So let's just take an example. Concrete Hamiltonian. This is a local Hamiltonian on a line of qubits. So these are my n qubits. I call it the EPR Hamiltonian. This is just an example. So think about this example. Imagine that my local Hamiltonian is like this. It's very simple. It's constraining every pair of nearest neighbor qubits to be an EPR pair. So it's just projecting each of these on the complement of an EPR pair. So I have all these terms that say this should be an EPR pair, this should be an EPR pair, and then I have all these terms that say this should be an EPR pair, this should be an EPR pair. So this is a highly frustrated Hamiltonian, right? Because it's impossible to have all these guys be EPR pairs and then also these guys be EPR pairs. The ground state energy is like a half of the number of terms. So there should be no way to succeed in my proof system or in my game if this is the local Hamiltonian. But in fact, if the only test I was to do is sort of the natural test, which is to choose a local term, this local Hamiltonian, and ask one Merlin about the first qubit, the other Merlin about the second qubit, then they would succeed always in my test. Because what they could do is just simply share a single EPR pair, and then whatever local Hamiltonian I'm interested in, they'll send me back this EPR pair, and then it's always going to work out. So this is why the consistency checks are important, right? This protocol by itself wouldn't work. And it's why instead of asking only 2 Merlins, each of them for 1 qubit of the 2 qubits that the local Hamiltonian is acting on, I'm asking them to encode this. And now maybe we're just going to see briefly why they're not able to fool my new protocol. This is what one thing they could try to do is just take a single EPR pair, encode that EPR pair using the 5 qubit here. I only have 3 Merlins, but it's the same 5 qubit error correcting code as before. Each get a share. Why is this going to fail? Well, so let's run the protocol. So if I ask all of the Merlins for the same term HL, then this is going to work because I'm going to get back in my hands the 3 shares associated with each qubit of an EPR pair, decode, check that it's an EPR pair, and this works out, it's also fine. But let's look at the consistency test now. In that case, I'm asking, I'm asking one of the Merlins for his 2 shares of the local Hamiltonian, and I get back these 2 shares. But then the other Merlins are asked either the matching shares for the leftmost qubit or the matching shares for the rightmost qubit. But they don't know which term I'm interested in. They don't know if I'm interested in this term or this term. So it can't be that they always, it's either this case, from their point of view, it's this case or this case. And so it can't be that in both cases, they're able to send me shares that complete into a code word with respect to what the first Merlin sent me in, both in the case where I was interested in HL or in the case where I was interested in HL minus 1. So this is trying to give you an idea of why they wouldn't be able to fool my protocol. In practice, it's a bit harder, though, and the analysis gets kind of technical. If you think about it, it also gets interesting, because what are you trying to do when you're trying to show soundness of such a protocol? You really don't have much to start with, right? What does proving soundness mean? It means, suppose that I have a Hamiltonian, local Hamiltonian, that's given to me, and suppose also that it's possible to succeed with very high probability in my game. So I have a strategy for the Merlins that succeeds in the game with high probability. And what do I want to conclude? So I'm trying to basically do the contrapositive, right? Suppose there's a high strategy, a high success strategy in the game. I want to show there exists a low energy eigenstate of my Hamiltonian. So I want to show you that that state exists. But how do I show that? I don't have much to start with. I have 5 provers, 2 provers, and from these I'm trying to construct an n qubit state. Where do I get n qubits? From only 2 Merlins or 5 Merlins. I don't have this locality structure that's given to me a priori. I have locality between 2 or 5 Merlins, but that's not n qubits, right? And so the proof has to show you this, how to show how from the strategy of the Merlins you can reconstruct an n qubit state, at least in principle. And so that's what our proof does. It says, well, here's your 2 Merlins, and they have some kind of a state in mind. So it's a tensor product of only 2 systems. And from this tensor product of only 2 systems, I have to come up with a tensor product of n systems. And so we give a circuit. We say, starting from the strategy of the Merlins, here's how you're going to construct a low energy state from your Hamiltonian, 1 qubit at a time. And so the first qubit is kind of easy. Because it corresponds to a certain question that you can ask in the game, right? In the game, at some point, with some probability, I ask the Merlins to show me qubit number 1 of the proof. So they have unitaries that are able to generate qubit number 1 of the proof after the decoding. So this is the decoding operation. So I know how to get qubit number 1. Okay, now how do I get qubit number 2? Because the problem is, I use these unitaries that the Merlins apply to their shared state when I ask them about qubit number 1. I know they also have unitaries if I ask them about qubit number 2, but they're not supposed to be applied after I apply the unitaries for qubit number 1, right? So what do I do next? It's not clear. I want to undo what I did, so apply the dagger of extracting qubit number 1, but qubit number 1 came out. I decoded it to get qubit number 1 of the proof. So I have to say, what do I replace it by? And what we replace it by is pretty simple, just half of an EPR pair. EPR pair doesn't matter. What matters is that it's the totally mixed state. And so the property that I'm using in order for this to work out is another property of the code, which is the property that the reduced density of code words on any just 1 qubit is the totally mixed state. And so I'm going to plug in a totally mixed state here. I'm going to have to argue that from the point of view of the prover, this one prover doesn't see the difference. He doesn't notice that I took out qubit number 1. So I can take out qubit number 2 now and repeat this procedure. Undo the fact that I took out qubit 2, replace it by the totally mixed state, and then extract qubit 3, etc. So you construct a circuit like this that extracts the n qubits 1 at a time from the proof, and you have to argue that once these n qubits, once these n qubits have been extracted, from the point of view of the local Hamiltonian, because it's a local Hamiltonian, looking at only 3 qubits at a time, it's not going to be able to make the difference between when I measure it on these n qubits that I constructed from my circuit or when I measured it in the game, the way the verifier would do in the game. And so that's basically the proof here. I'm not showing you any of the details, but this is how it works. I had a slide relating this to the quantum PCP conjecture, but I'm going to skip it because I'm out of time. We can talk about this later. It's actually pretty interesting, but I'll directly go to a summary and maybe a couple of questions. So just to summarize, the whole point of the talk was to argue that you could go also give this truly local verification procedure for the local Hamiltonian problem, where truly local is according to the definition that I gave you, right? In my own definition, you can give other definitions of truly local. An interesting consequence is that the fact that I give entanglement to the Merlins in these multiplayer games or interactive proof systems makes them strictly more useful to Arthur than they were known to be before. And the proof uses these error-correcting codes in an interesting way. Depending how you look at it, you can also see this as a way to use monogamy of entanglement. So there's been follow-up work on what I presented. In particular, it's a very nice result by Zhangfeng Ji, who's at IQC, that you can achieve the same thing. You can ask the question, is it essential that I'm getting qubits as answers from the provers? And actually, it's not essential. You can make this into a completely classical proof system where you only get a very small number of classical bits as answers from the Merlins. And this still works in the same way. So what's really essential is that they're able to share entanglement. They're able to share quantum states in their mind. This is essential. If I remove this ability from the Merlins, things don't work out anymore. But Arthur himself doesn't need any quantum abilities for this to work. Okay, I have a bunch of questions, but unfortunately, so I didn't describe this conjecture. The conjecture, actually, I can say it, the one with the star. This one I'm not describing. The conjecture, the open question there, is whether you can achieve the same thing as I described to you, but with a constant separation between the completeness and the soundness. I described to you a proof system that has completeness 1, soundness bounded away from 1 by an inverse polynomial. I'd like to do the same thing with a constant soundness. That's not known. We have sort of work in progress with Anand Natarajan, who's also there in the audience from MIT. We can get a constant completeness soundness gap, but unfortunately, we lose somewhere else. We lose in the size of the questions. The questions become very long. The answers stay of constant size. Questions become polynomially long instead of being logarithmically long in what I described here. Another nice question is whether you could go beyond QMA. I asked a question here about QMA because it's kind of natural, but we don't have upper bounds on the power of these multi-entangled Merlin proof systems. It could be that you can use them to decide languages that are beyond QMA. I would find it surprising, but before this result, I already would have said that I find it surprising that we can go beyond NP. So we can go to QMA, and maybe we can go beyond. I think that's an interesting question. Let's stop here.
Questions?
Is there any possibility of changing these to zero knowledge proofs?
It should be. I never thought about it. I'd imagine, because you're already not getting that much information out of the Merlins, right? Especially in the case where you imagine that reduced densities are totally mixed, which I would imagine is the case. So I don't know. I'm not an expert on zero knowledge. I want to give a straight answer, but I would imagine you could make this into zero knowledge.
Other questions?
So can you tell us a little bit about the relationship to quantum PCP theorem?
But I have to formulate it. Yeah, I can tell you nothing is known, so it's going to be short. So, well, I can flash the slide up. So, I talked about the classical PCP theorem. And, okay, this is going to be a little bit for experts, but not too much. So, the classical PCP theorem has two equivalent formulations that I gave you on my second slide. One formulation is that all languages in NP have the kind of multiplayer games that I described, where the gap between completeness and soundness is a constant. Another formulation of the PCP theorem is to say that given an instance of 3-SAT, in the worst case, it's NP hard not only to decide satisfiable versus not satisfiable, but it's also hard to decide between satisfiable and the best you can do is satisfy, let's say, 99% or even 90% of the clauses simultaneously. So this would be an easier problem, right? Because I'm telling you either it's fully satisfiable or only 99% satisfiable. But it's actually just as hard as the original problem. And these two formulations are equivalent, and it's easy to see that they're equivalent. The only idea you need is to think of this clause versus variable game that I gave you earlier. So in the quantum case, we can play the same game. We can say, okay, what's equivalent formulations of these two things, quantum formulations of these two things, and I gave you a quantum formulation of this formulation of the PCP theorem, which is at the bottom here. So it's what I call the quantum PCP conjecture star, which is that QMA has multiplayer games of the kind I've described with the quantum Merlins with constant completeness on this guy. What's called the quantum PCP conjecture in the literature is what I'm flashing up here, and that's a quantum analog of this formulation of the PCP theorem. It's saying not only is the 3 local Hamiltonian problem QMA hard to decide, when the promise is that the ground state energy is either, let's say, 0 for QMA1, let's say 0 or a bit above 0, inverse polynomial. So you're trying to distinguish between ground state energies that are an inverse polynomial far apart, but you're trying to say, hey, it's actually still hard to decide even when I have the promise that the ground state energy is either, let's say, 0 or not slightly above 0, but a constant times the norm, m here, think of m as the norm of the Hamiltonian, so a constant times the norm of that Hamiltonian above 0. So this is a pretty strong promise, right? Either 0 or constant fraction of the norm. But quantum PCP conjecture says that, postulates that maybe this problem is still hard. And so what's interesting is that, and so, you know, what I described goes in the direction of showing this conjecture, but we don't know how to relate them. The reason we don't know how to relate them is that this, what I said in the first few slides, that this clause versus variable game, you try to make it quantum, you get this Hamiltonian versus qubit game. It's not clear at all what the Hamiltonian versus qubit game is saying about the relation between these two problems. At a high level, we can't relate them because the notions of locality are very different. Classically, they turned out to coincide. Here, when I say 3 local Hamiltonian, I'm talking, you know, local is about these n qubits. Here, when I say local, it's about these 2 Merlins or 5 Merlins. But their local Hilbert spaces can have very high dimensions. Here, I kind of know that I'm talking about qubits or qubits. There are different notions of locality. And relating these two problems, to do it, you have to relate these two notions of locality. And that seems hard, but I'm not saying it's impossible at all. It's just we don't know. I think it's an interesting question. Sorry.
Other questions? Okay, well, let's thank Thomas again, and let's thank all the speakers from the